Okay, so let us continue our discussion where we left last time. So, we were looking at this defect reaction. So, here it is a non-stoichiometric oxide, basically oxygen going or escaping into atmosphere and leaving behind vacancy. However, like I said earlier that number of sites would remain fixed, the ratio of sites would remain fixed. The number of sites need not remain fixed, but the ratio of sites which basically is proportional to the M and O, that will remain as it is. And for writing that defect as a reaction, this is the reaction, and for that we get concentration of oxygen vacancy, and we also get concentration of MM prime, basically where the electrons are localized. So, here we had assumed localized ionization. Like I said last time that next what we will do is delocalize the electrons over here and then see how we can look at the equation and get a equilibrium concentration, because now we will have two different kind of species, one which is electron and hole kind of species, and the other would be vacancy kind of species, vacancies which are related to lattice sites, but electrons and holes, they are not related to, or they do not have on the denominator the lattice number of lattice sites. What they have is the N effective, the density of states. So, let us write down this equation, when similar equation. However, this time what we are doing is delocalizing. So, oxygen at oxygen site leaves behind vacancy, and since it was supposed to be negative with, so no actual absolute charge, it remains effectively positive, and it means 2 electrons have been left or have escaped. So, these 2 electrons remain as electrons, not localized on any metal site, and plus 1 by 2 O2. So, now we have 3 different kind of species, actually not even 2, we have lattice related sites, we have electrons, and we have oxygen whose activity is given not in fraction or not in fraction concentration, but in partial pressure. So, now how do we write the equilibrium constant? So, let us see, we will write it like this, K V O prime. For vacancy, we can still, the activity can still be related to the concentration fraction, and therefore, it will remain x. For the oxygen, we can still write x O O. Now, for the electron, the concentration ratio would be given as N by N effective, density of states, and since there is a factor of 2, so there will be a power of 2. And then for oxygen, like we said that the activity will be expressed as partial pressure of O2, and since there is a power of 1 by 2, the factor of 1 by 2, it translates to factor of the power of 1 by 2. Now, another thing that we know is that N, number of electrons, would be equal to twice the number of vacancy at oxygen sites, because each oxygen atom that escapes leaves behind one vacancy, and each of those oxygen atoms were associated with 2 electrons. So, there 2 electrons and the number of electrons would be equal to 2 times the vacancy at oxygen site. So, now here we have different denominators which are constant, and we need to club them together, and therefore, what we can do is pull them together and combine them into this is again a constant. So, we can combine them into this factor and name it a new constant as KVO double prime. So, we can make it KV double O prime. That is not the only thing, we will also do what we have always been doing, which is assuming that this is the dominant defect and oxygen the defect concentration is very small. So, assuming that this can be taken approximately as 1. So, the denominator of this, meaning this will become, with this we will translate to VO by NO, NO is the number of oxygen sites. Now, this is a constant, this is a constant. So, we will plug them together, we will pull it to the left hand side and club them together, and so now we have KVO double prime. So, this prime here is not for negative sign, remember, it is just to show that this is different from KVO prime, and KVO prime is different from KVO. So, do not confuse this prime with the negative sign, those will be associated with the components in the reaction. This is a rate constant. Now, we will use this over here. So, what you have here is N will be replaced by 2 VO. So, it will take a square, it will become 4 VO square, and this is VO. So, 4 VO square into VO is 4 VO cube. So, we will first write it like this. Which is equal to So, now we will rewrite this equation so as to get the concentration of VO, and this is nothing but and N is twice of this. So, if we write N in this similar formalism, it will come out to, so this will be multiplied by 2 and this is minus 2 by 3. So, it becomes 2 1 by 3, we can pull them together and it becomes okay. So, there is one mistake I committed here, we have to take cube root because it is V cube. So, this one becomes minus 1 by 6 because it is also going to the LHS and then we are taking cube root. So, it becomes minus 1 by 6. So, note that this is minus 1 by 6 and similarly here it will be minus 1 by 6. Now, this is a constant, but this constant is also related to the formation energy and entropy, and therefore, it has something like this. So, some standard constant, and with respect to that this will be so, if we want to convert it or if we want to get it into the similar formation or similar formalism as earlier in terms of delta H exponential of delta H, then we will convert this using this relation, and therefore, this N will be equal to and to take into account cube root. So, there will be a factor of 1 by 3 and since it is R, we are assuming that this quantity is given in per mole and this is also O2. So, this is also O2. And if you like, you can also write for the VO in a similar form. Remember, this double prime is not for minus, it is just to show that this is a different constant. And this constant has consumed in it these constants, the denominator here over here and this denominator. When we were using just the fraction, then you do not have a denominator, and therefore, we did not have this have to invoke this kind of formation earlier, this kind of equation form earlier. So, these are two similar relations, and this is not very clear. So, let me rewrite this part. So, these are two similar relations. The only thing is that n is twice of V naught and everything else in the quantity remains the same. Now, once we have this equation, we can do something more, which is plot it as a equation of PO2. And as we stated in the previous lecture, that concentration of oxygen vacancy and your defect increases with decreasing partial pressure. So, when you plot it, this would become even obvious. So, here on the x axis we have log partial pressure of oxygen, and on the y axis you can have log n or log vacancy oxygen concentration. So, how would this look like? If you look at the equation behind it, everything over here, assuming temperature is constant, if temperature is constant, then all these things are constant, the only thing is changing is P. But now, if you take it in log, then this is again a linear form of relation, and therefore, what you will have, if let us first draw the VO, so it will be a straight line like this. So, this is our VO, log VO concentration actually. And similarly, if you want to plot n, n is nothing but twice of this. So, it will come out like this, n is equal to 2 times, and this is proportional to PO2 to the power minus 1 by 6. So, the slope here, the slope that exists over here, both the slope is equal to minus 1 by 6, and the assumption here is constant temperature. This kind of plot is called Brouwer diagram. And now you can see what the equation is saying and what the reaction is saying, that as your pressure, partial pressure decreases, which is going in this direction, concentration of N and concentration of vacancy increases. And what you also can now see from this plot is that if when you take the log plot, then it is a linear relation, and you can predict the slope, which is equal to minus 1 by 6. So, you can get to know how much pressure, if you know the pressure, you can predict what will be the N, or if you know what is the N you desire, then you know what pressure to partial pressure of oxygen should be. So, this is a very useful diagram and is very important with respect to defect chemistry. So, now that we have looked at different kinds of defects, we looked at different ways of writing them. First, different ways of getting the equilibrium concentration. First, we used the entropy configuration, configurational entropy. Second formalism was using it as a defect reaction. So, when you use it as a defect reaction, then using the defect reaction you can again get equilibrium concentration using the rate constant and the equilibrium constant. So, using both of these, we saw that there are wide variety of defects that can be written as a reaction, and you can get equilibrium concentration for them. And in fact, in the defect reaction, I believe it is much more straightforward to get the concentration or the relation for concentration. Now, let us solve some problem. Now that we have looked at all the basics, of course, there can be more combinations and permutations of different kinds of defects, and now if you know the fundamentals, you can understand and you can take this understanding forward. Now, let us try to solve some simple problems on these defects. Let us say you are given that for aluminum delta HV is equal to 0.8 electron volt per atom and delta SV by R is equal to 2. You are, so this is example 1. And what you need to do is calculate equilibrium vacancy concentration at A 25 degrees Celsius and B 660 degrees Celsius. For aluminum, 660 is close to melting point. So, you are being asked that at room temperature what will be the equilibrium vacancy concentration, and at near the melting point what will be the equilibrium vacancy concentration. So, what we have is something like this: aluminum to vacancy aluminum, that will be the defect reaction for this, and in the simple terms, in this defect reaction, the equilibrium constant would be given by x VAL by x AL, and this will be equal to delta S by R. So, we are assuming that this delta S by R, delta S was in per mole, and therefore, delta S by R is given. So, it does not matter whether what is the final unit of delta S, because once you know delta S by R, it is equal to delta S by K if delta S was given in per atom, and exp minus delta HV by KBT. Here we are using K because delta HV is given in electron volt per atom, sorry, the unit should have been per atom. So, now this is the equation, and assuming that this is the dominating defect and the defect concentration is small, first approximation that we can do is we can take this approximately equal to 1. Now, we have XVAL. So, what we can write XVAL is as vacancy aluminum by Na. So, this will give you the vacancy concentration in per mole. So, this will become XVAL is equal to delta S by R is given as 2. So, it is exp 2, this will be constant, where this is this remains the same, and exp 2 will translate to 7.38. So, we have simplified our equation a little bit. Now, what we have here is delta HV. So, what we need now Kb. So, there Kb value is usually given, but if it is not given, then you must actually this is a quantity that you should remember, and this has, you can write it in different units. So, if you write it like this, actually it should be per mole. We do not need so many decimals. This is just to let you know, this is up to this extent it is known. So, this is in joule per Kelvin per mole, this is in electron volt per atom per Kelvin, and there is also another unit erg per Kelvin. Per mole. So, now when we know this, now we know this quantity, we know this temperatures are given, this is given. So, we can quickly calculate this and we will multiply it with Na to get number of vacancy per mole. So, first let us solve it for T1 equal to 25 degree Celsius, which is equal to 298 K. So, first you have to convert it to Kelvin. Now, this so, we are calculating at T1 equal to 25 degree Celsius, which in Kelvin is 298 Kelvin. So, VAL by Na is equal to 7.38 into minus 0.8, because delta HV is given at 0.8, and we will use the kb in electron volt per Kelvin. So, it is 8.6, will go only up to 617 into 10 to the power minus 5, and temperature as we said is 298. So, this will translate to 10 to the power minus 13. So, this is a fraction. Now, we will multiply it by Avogadro number, which is, now this is also Avogadro number is also something that you should know, is equal to, so when we have multiplied by this, then it is so many vacancies per mole, and it will translate to 1.311 into 10 to the power 11. Now, this looks like a very large number, but see, it is you have to note that it is per unit mole, and mole is 6.023 into 10 to the power 23. So, it is if you look at it in terms of fraction, it is 10 to the power minus 12th fraction, that is for each 10 to the power 12 atom there is one vacancy. So, this is a very small quantity. Now, let us do this calculation for 660 degree Celsius, which is equal to 933 Kelvin. So, VAL by Na, actually I should have denoted Na by uppercase A. So, let me write it like this. This is 7.38 into exp minus 0.8, delta HV is same, and kb value remains same 8.617 into 10 to the power minus 5, and temperature is different, which is 933. And when you multiply it with, then what you get is 2.12 into 10 to the power 20 vacancy per mole. So, what are the few things that you observe here? There is a very large jump in vacancy concentration. From room temperature to Tm, and this is expected, but even at, if you look at this number 10 to the power 20, this is still a very small fraction. Of course, it is much larger than this number, but if you look at it as per mole, then it is still a very small number, like 0.001, approximately less than 0.001. So, but this is still a very small quantity. at Tm. So, this is a big jump from room temperature to melting point, but this is still, as you can realize, is a very small fraction 0.001. So, we are not even reaching 1%, we are not even reaching 1%, this is less than 0.1% of the number of sites are vacant. So, that is the minuscule, that minuscule amount even at close to melting point. Beyond melting point, of course, there is no point in talking about vacancy concentration, because it will be in liquid state, and we have what we have derived is for solid state. So, this is the maximum vacancy concentration that you would see, assuming that these values are true. So, this is example 1. Now, similar type of example can be given to you in a different form. For example, you may be asked to calculate number of vacancies per cubic meter. Okay, so, it will be very similar, the question is similar, but it is given in a little different form: per cubic meter of iron at some temperature, let us say 800 degrees Celsius. Delta HV is equal to 1.08 electron volt per atom, and it is given that rho. So, these are some other quantities that you will need: 7.65 gram per centimeter cube, and what you will need is atomic weight, which is equal to 55.85 gram per mole. Now, if you remember the equation, number of vacancies by N A, then it is equal to number per mole. Now, if you multiply this Na, which is Avogadro number, into rho and divided by atomic weight, then what you have, this, the unit of this would become, and the density is, and for atomic weight the unit will be, so this is number per mole, this is gram per mole. So, what we have is mole gets cancelled, gram gets cancelled, and the unit becomes number per centimeter cube. So, we can simply multiply with this factor rho Fe. So, this is what we will do: Nv is equal to Na into rho Fe, and since we are not given delta S by R, we will assume that it is too small to be taken into account, and we will simply calculate like this. And what you will see is that you will get a quantity like this. And what will be the unit? Like I said, it will be number per centimeter cube. So, this is, like I said, same question, but put it a little differently. So, you have to apply yourself to see how to get the correct units, and here we have per centimeter cube, it is still not per cubic meter. So, we will multiply it with a factor of 6, 10 to the power 6. So, it becomes 1.18 into 10 to the power 24, and that will become number per meter cube. So, here what we are looking at is with a different units, we are looking at how many vacancies would be there in 1 cubic meter of iron, or if we are talking about centimeter cube, then 1 centimeter cube, something as small as this, what will be the number density. So, this is in 1 centimeter cube, these many numbers. So, again it may look like a very large number, but keep in mind that the number of sites are also very, very large. So, this will be a very small fraction, even at 800 degrees Celsius, it will be a very small fraction. So, we will come back and we will solve another problem before we move on to one of the other topics related to point defect, which is diffusion. So, we will continue this example solving in the next lecture. Thank you.